Now we talk about some variations of the depth first search, some optimization technique which will improve the incompleteness problem of depth first search. So the first one is called the depth limited search. So as I said, depth first search can fail in infinite state spaces because it might follow an infinite path. One way to prevent this is by giving DFS a predetermined depth limit denoted as L. So depth limited search treats nodes at depth L as if they have no successors. So you go to the level L and stop there. This solves the infinite path problem but introduces potential issues. One is that, again, incompleteness, some other type of incompleteness. If the shallowest goal lies beyond the depth limit, that means if the depth limit is up to 3 and the first goal or the shallowest goal is at level 4, then in this way the search will miss it. Another is non-optimality. If L is greater than D, that means the level you are trying to explore is, let's say the level is 4 and the depth of the tree is 3, in that case the search may find a solution but it don't necessarily be the optimal one. So you are kind of exploring the tree more than where the goal node is. So that way you cannot find the solution in time, not optimal. And the time and space complexity of this will be, it's very similar to the DFS. DFS is order of b to the power m, but here is b to the power l because here m equal to l. And the space complexity earlier was b times m because you store all the successors in the path in one path for up to length m. So here will be the path length is l, so it's b times l. That is still again linear. So optimality cannot be guaranteed. Depth first search is a special case of depth limited search, as I already said, and is for L equal to infinity. So we don't have any limit. We remove the limit L, then DLS becomes DFS. So we can view standard DFS as a special case of depth limited search. That's why. So choosing a depth limit is important. Okay, sometime let's say the problem structure kind of provides a natural limit. Like for this Romania map, it has 20 cities. So the longest possible path is definitely 19 steps, okay? Because in a MST, you know that if they are minimally connected, so there will be 19 steps to go from one city to the 20th one. But if we do a better estimate, that will be the diameter of the state space, which is the maximum steps between any two states. So like I'm just telling from Arad to Niamt. So you will find out that the diameter is 9. That means there is not more than 9 edges. So how many steps? Arad to Sibiu to Fagaras to Bucharest. So it's 5, 6, 7, 8. So it's not more than 9 edges between any pair of nodes. So the diameter is 9. So we can say that the depth limit does not need to be more than 9. So for many problems, the ideal depth limit is not known in advance. Please understand. For this graph, we can tell that for many problem is not known in advance. So we have to keep trying. So from this, now about the depth, how you implement the DLS. Depth limited search can be added as a modification to the general tree or graph search algorithm. So alternatively, it can be implemented recursively like we could have done for DFS recursively. It can terminate with two types of failure. One is standard failure when no solution exists within the depth limit, and the second is cutoff. That means no solution exists. One is that no solution exists. The second one is no solution exists within the depth limit. So the second one is not really no solution exists, but it's just basically nothing found within the depth limit. So we can still specify a very large limit L, and that will harm the optimality. So there is another algorithm which is called the iterative deepening search or iterative deepening depth first search, which is a strategy that combines the benefits of DFS and the BFS. So it addresses the problem of unknown depth limits in depth limited search by gradually increasing the depth limit. So you are not starting from L equal to 5 or something. You gradually increase, initially 0, then 1, 2, 3 in that way. And then you continue until a goal is found at depth D. So which is the shallowest goal node. So what are the properties? It's very memory efficient. Okay, so you increase the depth from 0 to in incremental fashion, and keep running depth limited search for every individual limit. So it's a recursive procedure. So you see at limit 0 you just visit probably RL, and then once visited you remove it from the stack. Then the next level, you are basically increasing the limit to 1, so you are checking the limit 0 and limit 1 nodes. Then if it's limit 2, then you are checking the limit 0 nodes, limit 1 nodes, and limit 2 nodes. And in that way you can do up to limit 3, where you do 0, 1, 2, 3 in that way. So what do you think? Is it complete? So it's guaranteed to find a solution if one exists. Okay, so provided the branching factor is finite. If you have b equal to infinity, then of course you cannot find, but otherwise yes, it is possible if the branching factor is finite. So what about the optimality? You will talk about the optimality first. If the path cost is non-decreasing function of depth, that is equal step cost, then it's optimal. Okay, so here we bring the BFSS concept. The path cost is non-decreasing function. Let's say for level 1 all the they are like all are 10, the level 2 all are 20, something like that. So level 2 will be higher, so non-decreasing function. So in that case you can say that okay, you find a optimal solution. It's possible if the path cost is a non-decreasing function of depth. Now about the time complexity, it's order of b times d. Okay, b to the power d. So which is very similar to what we did for DFS for up to the level d, b to the power d. And the space is again linear because you store at one path at a time, order of b times d. So so iterative deepening repeatedly performs the depth limited search with increasing depth limits, and it states at the states at shallower levels are generated multiple times. You can see that, right? Like in this example, like limit 0, limit 1 kind of generates BC, limit 2 again generates BC, limit 3 again generates BC. So any shallower level than the current kind of the border or the final state or the limit state will be generated many times. Okay, but this is not costly because the last level is the costliest. If it's a binary tree, consider at the level D, it will be 2 to the power d. Any level below that will be kind of half of the last level. So because most nodes are at the bottom level, so repeated generation of upper levels contribute little to total work, very few contribution. But the worst case number of node generated is again order of b to the power d, which we have already shown in the time complexity. So the time complexity is asymptotically the same as BFS. Okay, it's asymptotically same as the BFS. But with branching factor b equal to 10, the depth d equal to 5, IDDFS can generate 123,450 nodes. Okay, so that's kind of you see this numerical b equal to 10 and d equal to 5, IDS can generate 123,450 node, where BFS can generate a lot of lot more nodes. So the overhead is small relative to the total. Okay, so the total number of nodes, the overhead is pretty small. So what is the usage? The preferred uniform uninformed search method when the search space is large and depth of the solution is unknown. So this is preferred. So the search space is large, so it's kind of combines the good things of BFS and the DFS. Some extensions will be iterative deepening to BFS in exploring complete layers per iteration. You're kind of exploring the complete layers. There's a related idea. Okay, it's called iterative lengthening search. Which is here. So iterative lengthening search, which applies increasing path cost limits instead of depth limits. Okay, so like we did in UCS, you remember, increasing path cost limits, but it has higher overhead than uniform cost search. higher overhead. So that is the iterative deepening search.